Okay, wrong. All right. Thank you so much, Howard. And I'm sorry for the delay, but thank you everyone for joining in. So, this is going to be a presentation about deep representation learning or the current paradigm of representation learning with some theoretical foundations. And what we are going to do is we're going to look at the classical methods of representation learning and then like go from the classical methods to these current deep networks which are huge, show emergent behavior like the clip models, the vision based huge transformers, and all of those. So let's get started. Oh, I still can't change the slides.
What? So Zoom is having problem?
Yeah, Zoom, I think it's a problem with Zoom. Okay, now
I
you
think
can?
yeah, left,
Okay,
left,
okay,
right.
cool. All right. So what are representations, or what is the representation learning problem? So how do you define a representation? The best way to define a representation is something that makes your task easier. Let's say if your data was something like this in a higher dimensional space, and you want to classify these points based on their color, based on green or blue, and you want to do this in the simplest way possible, so ideally with a linear classifier that just separates these points out. And according, like with machine learning and all, the best we can do are linear classifiers, svms, kernel machines, but they more or less tend to like linear solutions. So our best bet is to take our data, project it onto a space in which the task becomes easier, so it becomes like linearly separable, and things like that. Now, what do we want our representations? What properties do we want our representations to have? So in traditional machine learning, somebody used to give us good features of the data and used to tell us that these are all the features that you'll need given this data set, and you can do any possible task with those features. So ideally, when we learn these representations, we want to do that. We want to learn generalizable representations that can be transferred over tasks, where once you learn the representation, you can basically throw away your entire data set, and now you can just work with these lower dimensional representations. Now, what is the motivation behind this? The motivation is from neuroscience. What people found out that irrespective of the sensory modalities, like here they had used in this Nature paper that they had used two different tasks. One was tactile sensing, the other was visual inputs. And what they realized that these representation, or these different modalities had a shared representation, in the sense the areas in the brain or in the cortex that lit up while doing these different tasks were more or less similar. So we basically, that the hypothesis is that you have a higher level representation which is common over modalities. Next, like we can define these good representations apart from the fact that they should be higher level or abstract enough that they can go over different tasks or sensory modalities. We want them to capture certain characteristics in the data set and make the data set easier. For example, in this Swiss roll example, you know that this data actually lies on a manifold, and to actually traverse this data set, you'll have to take the geodesic distances and move over the manifold. But what the best that we can do, or the easiest thing to do, would be to move in an Euclidean space. So how would you actually embed this manifold, which is in a higher dimensional space, to something simple like a Euclidean space where you can move easily, like, or you know how to move in a Euclidean space. So now, so now that we kind of have motivated representations, or why do we need representations? Let's see what are some characteristics of good representations, or how do we say a representation is good? So the first thing we want is smoothness of the representations. We want inputs that are similar to have more or less similar representations. So if you have x and x tilde, which are similar, or they are either augmentations of each other, or they're related in some way. We want the representations to also reflect that relation, or reflect this higher dimensional um, higher dimensional behavior or structure in your lower dimensional representation. Second, you want to capture all possible characteristics of the data set. You want to see in what all directions does the data vary, and you want to capture all possible variations of the data set. Now, once you do this, if you have captured all possible variations, then you can ideally use these representations for any task because you have captured all characteristics of the data set. And the other aspect is to encode them separately. Now, why would this be useful? If you have noise in certain dimensions or certain factors, you can ignore those factors and use the other factors. Moreover, some downstream tasks might only need certain factors for classification or any kind of modality or any kind of task. So then you can just ignore the other factors. Next, for like time series data set. Now, for time series data set, how do we characterize these good representations? These representations should like vary slowly over time, or you want, or if your time series is such that it's like Lipschitz continuous, you don't have like very crazy peaks or very sudden change in directions. You want more or less these representations to change slowly over time. Second, these representations should actually kind of uncover the hidden Markov structure or the hidden factors of the data set that create this time series. So any time series actually is, if you take a higher or a higher level representation, has certain structure in it which we want to capture. So these are like some of the characteristics of good representations. Also, please feel free to ask questions if something is not clear, or some motivation is not good, does not make sense, or if you want more motivations, like what else should representations have, and so on. So next we look at the evolution of representations. So people did look at these representations, or how do we learn important features of the data set. So the classical approach was PCA, principal component analysis, matrix factorization, and so on, where you took the data and you learned some statistics or characteristics of the data set irrespective of the labels or the tasks for which they were used. And these were usually like lower dimensional representations, or representations in which the data sort of separated out certain variations with each other, and so on. But most of these classical approaches were limited to linear projections. So in the sense, so they are insufficient. So when we had the machine learning paradigm where we just had features and like somebody gave us handcrafted features, these worked well. But now we have unstructured data, or so now what we actually need to do is we need higher level representations, or we need like multiple scales of representation. So now the deep learning approach, this deep learning approach, representation learning, has been used in all of these big models like CLIP, BERT, Llama, JEPA, and so on. So this is trained using unlabeled, unstructured data. And the main thing is these models actually, with deep representation learning, they can show emergent behavior. Like now these representations can actually do zero shot generalization, which is what we wanted. Use these representations for different tasks. In context learning, which is basically given a few number of examples, you learn certain relation between those examples and apply it to new examples, chain of thought reasoning, and so on. So now the key challenge is, we know that these large language models work, or they somehow work. They don't work in certain cases, which we'll discuss later, but if they work or when they work, we want to understand how these work and what is it that they learn really. So we will look at representation learning from two aspects. One is reconstruction based, aspect and the other is joint embedding. So reconstruction basically is data compression. Like, can you take the data, compress it, only keep information that is really informative about the data, and then use this compressed data to reconstruct the input? Does this learn good representation? This has been the foundation of PCA and so on, basically data compression. The other one, which is the current paradigm or the more recent paradigm, is joint embedding. What we want is basically this tries to solve the smoothness problem or the smoothness characteristic of representations that we want. We want basically data or we want representations which are invariant to data augmentations. And what do we mean by data augmentations? Is basically we use some domain knowledge. Let's say we know the data, we have some domain knowledge. If we change this data in a certain way, does the information change, or will this data behave differently for specific tasks if we do these augmentations? And if the answer is no, if the information more or less remains the same after these augmentations, then you can use these augmentations to learn this representation, to say that these examples are similar and you want them to be encoded together. So these are like the two paradigms which we'll talk about. We'll first talk about reconstruction and then joint embedding. So for reconstruction, the earliest methods were autoencoders. So basically with autoencoders, this is your loss function, where basically W1 is your encoding of X, and then you decode that representation. And then you see how well could you reconstruct your data from your lower dimensional encoding. You also have certain regularization on the weights to avoid overfitting. Like, you don't want to exactly capture every characteristic of every data set, or you want information that is common to all data to not be encoded really, because it doesn't give you any information. And then you see that the ideal solution, this is a convex optimization problem if R is regular. So with this convex optimization problem, we know that a global minimum exists. And since this global minimum exists, what is this global minimum? So basically, what this tells us is these ideal features are the same as PCA or the same as principal component analysis. What they do is they take the data and they find the directions in which the data varies the most, basically, has the highest eigen values. So this pk of X is basically the projection of the data onto the k largest directions corresponding to the eigenvalues. And it's basically the same as PCA, or this is what they found out. So now this gives us more or less similar representations as compared to PCA. Then what people came up with was denoising autoencoders. Let's say if you didn't just compress the data, but let's say if you added some noise. So here your input data is added, or some noise A is added to your data X. And now what you want to do is, along with compression, you want to denoise this data set, or you want to actually figure out, or by the action of denoising, you want to learn the structure in the data set. Like, how would I have to denoise this example such that it looks like an example from our data space? So now if we
Vaishnavi,
have this as an objective function, then you actually have this optimal representation or this optimal encoding or this weight matrix, which is similarly projects onto the k most informative directions or the eigenvectors, but you also have this noise vector in your pseudo inverse over here. So it does heavily depend on the noise, on the noise vector. So basically, now
hello.
you have something slightly different than PCA. You have different representations.
Vash, I
And you
think the
get
slides are not moving.
added over here. So these are
Hey,
like the two different
can you hear us?
or autoencoder based paradigms.
I
Vaish,
think
just hang on,
it's
hang
moved.
on 1 sec. The slides are not moving, so I think people are having a hard time.
Sorry, yeah,
Ah,
this was
thanks.
behind. Uh, is this better now?
Yeah,
So
just
yeah, we
changed.
can go.
Yeah, looks like we are on the same slide now.
Yeah. I'm sorry about that. Yeah, this is just slow. Sorry about that. Okay. Do you want me to go over any of these again? Um, no. Okay. All right then. Yeah. Actually, that would be better.
You need two PhDs to work with Zoom.
All right. So now we next. So now we can play around with noise. And how do we play around with these denoising autoencoders? Some like denoising autoencoders basically worked well when the data was simple, like your background was similar and your there wasn't like too much variation in the data set. But now for real images you have a lot of variations, and it is more or less very difficult to figure out what are the important variations just by compression. So now the kind of noise that you have to add actually changes. And the way people did this was by masking. So they use these masked autoencoders. You basically define a mask over certain parts of the image. And what you want to do is based on the context or based on the rest of the image without the mask, you want to try to predict. You want to try to predict the masked portion. So in this optimization now, you basically X, you multiply with the mask instead of having additive noise. But and you want to actually only predict the masked portion, or you want to calculate the loss only over the masked portions over here. So now what kind of or what kind of representations does this learn? Basically, these representations now are also informed by the context around it. So these kind of learn, or basically now the representations are conditioned on the context. Now you actually learn these representations, or how do the different representations, let's say representations of this mask, how do they depend on the context? So basically now you're comparing between different parts of the image and their representations. So people did this where they only used the L2 loss, but then the images were very blurry, or the mask portions, whatever that they tried to predict, were very blurry. If they used only adversarial losses is where you just try to predict a patch which looks really good or looks very realistic. What they realized was if you just ask the patch to be realistic, it did not quite depend on like the rest of the image really, or basically did not use the context to predict that patch. And when you did both sort of, then you get like a good masking. Or so basically what the adversarial loss constrains the model is to get to a representations which is realistic, which can lead to like realistic images. So these masked autoencoders have also been used for representation learning, and they do pretty well. So this image is from, or the image on the left, on the right hand side, that is from a previous denoising or masked autoencoder paper where they use convolutional neural networks. And on the right is the current masked autoencoder regime, which in which the architecture actually is a transformer architecture. So now you still do the same, but now with the transformer architecture, we see that we can actually uh, mask out a lot more patches than earlier, but you can still learn good representations from this. And this is based on that for every patch, you get more or less a one-to-one correspondence between the representation and that patch. So basically, the transformer architecture helps you a little in learning these representations. So now let's look at some theory on this autoencoder based representation learning. So basically, if you use there's this pack based theory, which I won't go into the detail, and you don't have to really look at this theorem, but I'll tell you what do you need to know from this theorem. But basically, from this theorem, you see that if you have an over parameterized regime, in the sense, if your number of parameters are much more than your data complexity, or basically more than the number of dimensions in your data, in the sense, for a system of linear equations, if you have many more variables as compared to the equations, you can have many possible solutions. And now when you have many possible solutions, in this regime, how does the generalization error look like? So this generalization error is composed of two parts. The first part is basically the bias of the error or of the predictor, and the second part is the variance. Now, one crucial thing to note is this C. C is given by D by N. D is the dimensionality of your data, or basically how many variables do you have, and N is the number of samples that you have. So C greater than 1 basically tells you if it's an over parameterized regime or not. So from the traditional bias variance trade-off, we remember this curve, right? Where if your model capacity is not enough, you underfit the data. The test loss goes down, but then it goes up. Like if you keep increasing the model size, it does not do super well, like once it has reached the generalization error over here. But the training loss can keep going down. But what people recently realized is this double descent curve, where the test loss after going up goes down again. This is the second descent, which is in the over parameterized regime and is the modern interpolating regime. So basically what it tries to tell you is, if in your model and if your training regime, if you have the number of parameters which greatly exceeds your dimensions of your data, or the number of if the number of variables greatly is larger than the number of equations, you get many solutions, and out of that, deep learning sort of goes to a good solution which generalizes better, which is given by this test error, which is lower than this test error. This. So now this double descent thing was found for supervised regimes, but now for unsupervised regime, you also see this. But there is a small caveat. So the test error actually keeps going lower as you increase K. So K is basically your bottleneck representation. If your bottleneck representation keeps going larger and larger, your test error will go down. Like, it will go down only if you also increase the model capacity. So as you increase K, you will see this double descent curve as you also increase the model capacity. So the basic thing or the basic takeaway from this is, if your masked autoencoder or any autoencoder based representation learning isn't giving you good results, isn't giving you a good generalization error or something, you either increase your data set size and keep training it for longer, along with increasing your bottleneck K or bottleneck size K. So the error crucially depends on both of these. It depends on K and it depends on C, the bottleneck size. Or C is the over parameterization regime. So increase your model size. So this was basically what they wanted to show for the autoencoder regime. Now, this double descent, crucially, this double descent is what gives these huge models their emergent behavior. And what do I mean by emergent behavior? It is in context learning from a few examples, zero-shot generalization, chain of thought, cross-domain knowledge transfer, and all of these that you see with GPT and Anthropic's Claude models and all of this is because of this emergent behavior, where you have really large models and relatively fewer data sets, or the size of the data set is relatively smaller as compared to them. So, so the whole point of this was use larger models, like just use larger models, train them for longer, and just ensure that you see this double descent curve. Okay, so any questions so far on the autoencoder based regime? Yeah. So far people have seen the double descent curve. I don't think anybody. So actually, very, very interestingly, the double descent curve was because somebody accidentally kept their model running on for like much longer. Like instead of like 1,000 epochs, they had like 10,000 epochs or something, and then they saw this behavior. So I don't know if somebody has tried to like do it for more, but I think we're kind of hitting the capacity. Because if you look at the scaling laws of the current GPT or all of these models, it has saturated. Like now, even increasing the model size is not helping. Increasing the data in according with it is also not helping. They're more or less really saturating. So I doubt whether there'll be another descent after this. And we haven't even seen the second descent go up, actually. It has consistently stayed lower.
Looking at it, convex behavior, it would be weird to like just be twice that it's like it should be either convex going down and then
So it is not actually convex, right? Like the deep learning models. Oh, you just mean about the loss curve?
yeah, but
So you're saying because this is convex, like why is it going down again?
yeah, it might be for like random initialization.
So this actually they found, I think they averaged over the initializations. Like so speaking of initialization, I don't know if you have read the lottery ticket hypothesis paper. So basically what they said was your random initializations actually really, really matter. In the sense, like there's some neurons which are like the winning neurons, which really give you good solutions, and the others basically do nothing. And these winning neurons don't change too much from your initialization. So basically, initialization is very important, but I think they see this over multiple different initializations. And actually, currently, the way people initialize it is very close to zero, or they initialize it with a zero mean, not unit variance, but a very small variance Gaussian. So it is like sort of averaged over a lot of initializations. So this is not an artifact of just the initialization, I would say.
Last talk by Tom Golden this year,
Mhm.
he talked about this double descent behavior, and he also mentioned some paper. Theoretical explanation about this descent.
No theoretical explanation
Yeah,
about
it's just a phenomenon they observed.
so so for these, like if you make certain like simplifying assumptions, like if you replace a deep neural network with like a kernel function or something, you can solve some of these optimizations, like, or you can find like the global minimum of it. And this behavior is still like you still see this behavior over there. So it is like they have found this and now they're trying to use theories to explain this, but like where does this really originate from or something is not quite like, or not formally theorized about this. But this, like the interesting thing is this phenomena is observed even in supervised learning and unsupervised learning. Like over here, really, all we wanted the model to do was denoise, and yet you see this behavior. So it is something. So this phenomena is a little bit because of the gradient descent characteristics. Like gradient descent tries to find minimum norm solutions, or given a lot of capacity, gradient descent will try to find like good solutions. Which so this is the validation loss. The dotted one is the training loss over here.
Yeah, I also have one question. So, as we are in the robotics and event camera, we cannot deal with like trillion size model, right?
Yeah.
So I'm curious about so can we go back to the previous page? Yes, exactly. So with the mass autoencoders, we know that there are like huge transformers like Swine transformer, like, but does this, right? But is there any success case with like a much smaller model that has this kind of behavior? Or it has to be.
So emergent behavior is mostly like in the over parameterized regime. So I don't think people have tried this, but ideally, if your data dimensions are lower, then you can probably get away with a smaller model. But I would also say if you really want a smaller model, just for training, start with a huge model. Use the lottery ticket hypothesis to actually sort of compress the model or prune the model.
Yeah.
And then it can work. But I don't think people have tried this or the masked autoencoder regime actually with transformers with like smaller models. Also, the transformers don't really work with smaller data sets. Like you need a lot of data to train them.
Yeah, so if we go to the emergent behavior page, that the assumption now is only over parameterized large model has this kind of emergent behavior. So and now they have this smaller model, like we said, the distill model that are few million, 100 million parameters that also have this kind of behavior. So is that due to distillation from bigger model, or is that like, I don't know, how do you explain it? Because the smaller model does not cover the whole data set, of course.
So with smaller models, like are you saying this?
Between 0.9 be like small, like they.
So I think they did use distillation, right, to
Yeah.
train them. Yeah, so if you use distillation, you basically with distillation, you're trying to model the bigger model's behavior. So ideally, the bigger model at convergence has found really good solutions and has found the smaller norm solutions. So if you're trying to model that behavior right from the beginning, you'll be forced in the smaller norm solutions. So I'm assuming that because of it's being trained specifically with distillation with a much larger model, they work. I don't know if you train them from scratch, if you will see this. Like, I really think it is because of distillation. So ideally, if you want to really train a smaller model, start with a much larger model, but have regularizations. Have regularizations which will force a lot of parameters or something to go to zero. And then you will still have something, but give the model the capacity that if it needs, it can use that capacity. If you start with a smaller model, you're basically forcing the model to also like to interpolate in a very bad way, such that it has to like or do the best it can with the current data set. So yeah.
So I'm
Yeah.
assuming that the old parameter systems, there are a lot of redundancy of theorems.
Yeah. Yeah.
And distillation is basically like training on those redundancy
Yeah.
theorems.
Yeah.
We add them on previously. That's.
So I didn't get your question. Sorry. So like.
So, yeah, so, my question is like, is over-parameter systems like always have redundancy, like huge amount of redundancy? And if so, why we should go for over-parameters system in the first place and not from other parameters?
That's a very good question. So like because this is like the space of parameters is very, very large. Your initialization really matters. over here? Like where in that space, in your complex loss function, where is it that you initialize? And sometimes with those initializations, like the lottery ticket hypothesis again, what the lottery ticket hypothesis says is some parameters that are the most important barely change at all, like as in the course of training. So by increasing the model size, basically what you're allowing it to do is give a lot of possible options or have many more neurons which can be initialized well, such that during training they can be active and contribute. Like if you have fewer neurons with the loss, more or less they have to change, or if you have fewer neurons with the loss function, they end up changing. They could change to a good place, but they could also change where, like to a saddle point or something like that, where it's not very useful. But ideally here with a lot of parameters, you can get good initializations, or you can get multiple initializations which could be good, or many possible initializations.
Scale it down to a small model,
Yes.
like going away or layers and so.
Not whole layers actually, like certain neurons or certain neurons in a layer.
Yeah, but I'm seeing that, right?
So with the depth, they haven't done anything, but with the width, you can, with the width, yeah.
First paper strongly emphasizes hierarchical representation.
Yeah. So there hasn't been like a lot of pruning in terms of layers, the
Right,
number of layers.
And well,
Yes. So
but explain the large difference. Something over.
yeah, so I would like for this definitely suggest looking at the lottery ticket hypothesis, look at good initializations. Like there have been certain good theoretical works on how do you initialize a model well, such that more or less it is close to the solutions that deep learning models would find, and with that you can get certain guarantees about your optimization. So good initialization and using a large model, at least at the beginning, could be good, or is basically necessary for this emergent behavior. Right. Okay, so all right. So now we next look at these joint embedding methods, which this is the regime which most current big models use as pre-training, or basically all these models are pre-trained with lots and lots of data, and this is what these loss functions are what they want the models to do, or what the models are trained on. So the core idea is again the smoothness constraint. Similar inputs should have more or less similar representations, and by forcing this, you're uh, imposing certain inductive biases in your representation learning algorithm. So this clip on the left, we have the clip model. What it basically tries to do is it tries to learn a joint embedding space, and the representations of the image and the corresponding text should be close to each other. So this is how they basically train their model. Now, this is not exactly unsupervised because you still have paired data, like you have images and you have corresponding captions, but the idea is the same. This is across modalities. If two modalities more or less give you the same information, then you want them to be similar in your joint representation space. On the right, we have the SimCLR model, which basically tells you that given an image and given two augmentations of the image, such that these augmentations do not really change information that you really care about. So they don't really change the structure of the data set or something. They keep the information that you really care about the same. And now what you want to do is map this to the representation space and maximize agreement. You want these representations to be very similar. So this is like the higher level of why do we need these joint embedding methods. So now with these, so one problem with these joint embedding methods is this. You want similar examples to have close representations. what stops you from actually learning a trivial representation for every example? Like just learn a constant same representation for every example, and basically your loss is like minimized. You're doing well. But that representation does not really give us any information, right? So, so now you have these two different methods. One is non-contrastive methods. So non-contrastive methods, the key idea is you want to align the representations of the augmented pairs, but with key one key aspect, which is you want representations to be similar, but at the same time, you want the different features of the representation to encode different information. So this is enforced by using this cross correlation matrix. So each feature should be decorrelated with every other feature. And now if you enforce this cross correlation matrix to be the identity matrix, now you're enforcing the representation to actually encode something, or to encode different things in different representations. So now you can't learn like a constant representation for every or all of your data set. So critically, this regime of contrastive methods or non-contrastive methods or joint embedding methods does not need negative pairs. If you have like in contrastive methods, people want like positive pairs, the representations that you want closer to each other, and negative pairs where you want your representations to be far apart. But here in this regime, you don't need negative examples. Basically, by enforcing the representation to be informative and decorrelated, you can actually get pretty good representations. So this is one. So this is the Barlow twins example, actually. So this does well. And in contrast, we have the contrastive methods, which pulls together views of the same example, but also importantly pushes apart the representations of different examples. So now we want to learn a nice metric space where similar examples are closer, but at the same time, different examples are far apart. And now if you do this, again, you can't learn like constant representations, more or less. So this is again like the SimCLR model, where you want the positive pair or the two the two augmentations to have, or the representations of the two augmentations to have very high similarity as compared to the negative pairs, like of that example with the different examples. Now the question is, how do you like calculate these negative pairs, or how do you come up with these negative pairs? If you do this in the unsupervised regime, you can't always guarantee that your pair will be negative, but more or less with a large number of classes, you usually get negative pairs. So this is the problem. You cannot sure shot get very good negative pairs or definitely negative pairs, but more or less this works. So ideally, if you were to really learn good representations using contrastive methods, I would suggest using the Barlow twins from the earlier example, where you don't explicitly have negative pairs, but you still learn like good representations. So now we can look at how, since most of you guys work with time series data sets, how do we learn this contrastive learning in time series, or how do we generate these positive pairs and negative pairs in contrastive learning? So basically, given any video over here, they try to sort of figure out which frames have a high motion window. And what they do is they create these positive examples and negative examples. Positive examples are where the frames are in the right order, or basically something happens, or there are no like, or there is continuity in the action. Either it can be in the positive direction or in the negative direction. Whereas the negative tuples is what you get by like permuting the frames with each other. So there's no continuity basically. Like you can like it's very fragmented. And now what you make your contrastive learning algorithm do is classify whether the given bunch of frames to you, are they in order? Are they in order, or are they not in order? Like, do they actually represent a good action, a continuous action, or some discrete fragmented frames of a video. So what this forces the model to do is actually try to understand or encode these continuous actions, or to figure out how or what makes a video or a continuous or a time series have these smooth representations which change like smoothly over time. So this is permutation contrastive learning. Next, you have something called time contrastive learning. Basically, what you do is you want the representations of nearby frames to be similar, but you want frames that are far apart in time to have some difference in them or some distance between those representations. So you create positive pairs with like close by frames and negative pairs with like far away frames. So this is like time contrastive learning. So how much time do I have? Okay, we're doing okay on time. Yeah. So very, very interestingly, this time contrastive learning actually helped solve one of the very fundamental problems of nonlinear ICA. So ICA is a very, or nonlinear ICA is a very fundamental statistical learning problem, which was unsolved for many years. But what they realized is you can use this time information. So here in this contrastive learning, they get labels because the frames are like numbered, or basically because you have some relation between which frames are closer to each other or which frames are more immediate and which frames are far apart. So because of this, you actually have some labels and you use these labels to learn good representations. So, okay, so this more or less like finishes the joint representation regime. Now, there are two things. With the reconstruction regime, you enforced your representation to actually encode everything about the data set, like all possible information about the data set. The joint embedding regime, you just said that similar examples should have similar representations, but you never enforce those similar representations to encode all of the information about your data. Basically, it can pick and choose. It can pick what information does it want to encode, and there is no constraint on it to encode all possible factors of the data set, which is one of the critical things that we wanted our representation to have. We wanted our representation to be really informative about the data set. So now, as a kind of solution, or a good solution, but as a solution to it, Jan LeCun came up with this joint embedding architecture called JEPA, where what you do is you do both these things. You do some sort of like, you still predict, or you do something in the latent space and not in the image space like autoencoders, but at the same time you're forced to encode information. So what this JEPA does is, if you take an image and you mask out certain portions, like the masked autoencoder, you mask out certain portions, you take the context and you encode the context. And now, given this context, you are asked to predict only the representations of the hidden part or the masked portions. So earlier in like masked autoencoders, you were expected to actually produce the image, the actual image with all the details and everything. Here, you're just asked to like predict the representation of the hidden part. So it sort of does both. Like given the context, you're supposed to use the context to interpolate or do something to try to predict the representation of the masked portions. So to the right, we have certain like some examples where this is the image, or the first column is the image. The second column gives you like the masked portions, like that part of the image is masked during training. And now what you expect or you want the model to do is try to predict the green box from the original image. So you try to predict the green box, and you see that more or less it sort of captures the structure, or it sort of captures what should be there, or at least, if not the exact details like the color or something, but at least the shape of the things. So it kind of captures what is it that you want to encode, or what should be the information over there, if not the exact information, just what kind of information should be there. So you see that like it is not perfect, but at least it gets the essence of the image from the context. And this sort of enforces it to like to have a representation space where you can do this kind of interpolation, where given the context, you try to predict the mask portions. So this is the current state of the art in representation learning, which has been used by a lot of papers for pre-training the models. So now if you want to do this for videos or for time series, a very easy thing that you would do is given given some frames as context, try to predict the representation of the future frames, or try to like, or can you actually predict the future given the context of the current frames? So this was actually already done. This is the excellent paper of contrastive predictive coding, where what they tried to do was given the earlier part of the time series, instead of predicting like all the details of the future frames, just try to predict in what direction is the future frame heading, or what do you expect to happen in the future frame. So this is basically, so given all these representations until time t, you want to predict the representations of the future frames. So this is what ideally should have happened, right? But what JEPA came up with, the video JEPA part of it, is something slightly different. Basically, you still mask the image to try to encode some spatial features along with the time domain. So first, in the first part of JEPA, so it's a two-step training process. In the first part of JEPA, you still do, or video JEPA, you still do the mask prediction to get spatial features, or try to predict the spatial features frame by frame. So if for one frame you mask out certain part, you mask out the same part in the future frames, and then you try to predict each. So ideally, you only more or less need the current frame and a few frames before and after to be able to like predict this. Now in the second part, what do they do is they keep this encoder frozen, but what they actually train is this predictor model where given certain frames, can you predict the future if I tell you what action is being done over there, or what would be the robot actions, poses, and so on. If I give you this information as a context, will you be able, or can the representation actually predict what will happen in the future? So this is the part which actually is similar to contrastive predictive coding, where the representations evolve over time, but now they're conditionally evolving. Like you're explicitly telling them what is going to happen, and if you tell it, can the representations work well? Which sort of makes more sense than contrastive predictive coding, right? If someone were to tell you that an object that was moving was suddenly hit by some other object, the earlier object will change its direction or something. That for that you need this extra information. So this is like the current state of the art in video encoding. This is called video JEPA 2, and for video encoding, this is something that they've been or this is the state, or the current state of the art for this.
Video chat of AC and what architecture we're using on.
So it's still a transformer. Yeah, they're all transformers. So I know that there were like some diffusion based video architectures, but apparently even in the diffusion based models, in the architecture they use transformers. Then they realized they don't quite need the diffusion part, so they came back to the transformer architecture. So they still use the transformers over here. So okay, so any questions so far, like until like yeah, any questions? Yes.
Exactly, this is the conditioning based on set of features to produce new frames is very similar to the idea of like diffusion. So I'm wondering what exactly is the difference between this and the transformer, like high level?
The diffusion?
Yeah.
That's a good question. Are you talking about specific diffusion models for videos?
diffusion is also like giving a set of noise, and then you give a set of like instruction, like the robot actual forces, they will search all the possible domain of the pixel and then generate this image to you, right? This also feels like even a set of encoded things, and then give it a constraint, it generated another image. It feels very similar to the diffusion. So you said that they tried diffusion and then end up didn't use it. So what's the difference of this and the diffusion, and why do they like? Yeah, what was the high level difference?
So, a lot of diffusion models are sort of like the masked autoencoder regime, where you try to predict in the image space and you sort of not masked, actually denoising autoencoder, where you add Gaussian noise and you try to denoise it. That is in the pixel domain. And sort of that training dynamics or that optimization is much more difficult, as we saw even in the masked autoencoder or the denoising autoencoder case. Whenever you have to produce certain details in the image, it is much more difficult. Whereas over here, one is the transformer architecture is sort of discretized. You create patches and you more or less like it's discrete in nature. And the second is this specific JEPA architecture. The important thing is you only try to predict the representation. So you don't really care about the details. You don't care about the exact details or what x-axis did some like the object end up on or something, but just an idea of what should happen. And that I think helps it see like the forest or let's say look for the trees given the forest or something like that. In the sense, it does not let it get lost in the details, but more or less capture the physics behind it. That is my thing, because I had the same question. Why not contrastive predictive coding, which did more or less similar, or this also did, and why this, or why not like diffusion based like denoising autoencoders versus this. I think this really like this the transformer architecture, you don't want to change too much. You only want to change this small architecture which tries to predict the future. So it is a much smaller model to train with lesser variables for change, I think.
So in Ghana, so is he only is he the only one, the lab that's doing the word model using this discrete representation rather than like frame? Because does this feature lead to some concrete future frames like the rest of the word models?
Uh, yes, but like we showed for like these joint embeddings, it is not exact. If you map the predictions to the actual image space, it is not exact, or it does not actually really fit too well with the image, but it more or less captures what is there. So even with the video, you don't see the videos being very great, but you more or less see that it captured the time dynamics of the video.
Yeah, so like with other labs doing the work model, like they train on future frames, like concrete frames, right? Like they can use a robot like the Google Genie, they can play in the world, you can push the button, the character moves forward, camera moves forward,
Mhm.
and generate new frames that's smooth with the previous frames, right? This cannot do that, right?
No, this cannot. Yeah. This is just for representation
Yeah.
learning. Yeah, I very much doubt that. So for that, I think generative models would be much better. And then diffusion model again. Diffusion model, flow-based models, because in flow-based models you can have like constraints, like really good constraints, and then you can do exact things. This one is more for abstract representations, to more or less get a sense of what is going on or what could happen.
Yeah, there are in some 3D worlds, some structure, size of the object, again, like one word model.
Oh yeah, but yeah.
Which one do you think is best? Well, with.
No, but I think a recent paper by Alexei they also try to do something similar, and they have better results. But just I think this one showed better results on a variety of downstream tasks, which sort of makes sense. You don't need like pixel level coherence for a lot of these downstream tasks.
How do they measure this is better than the other since they are not producing completely?
Oh, you use them for like things like segmentation. For segmentation, you don't need like exact things,
Yeah.
or you basically use the unit architecture. The unit transfers more of the details that you need, and only like the changes are being there. So they do it for segmentation, they do it for tracking, object detection with tracking, and so on. So they do look at the downstream or the downstream results on a number of tasks for this.
So and this embedding on our patchwise, the
Uh,
representation that we get is over the whole image or patch?
No, yeah, patchwise. It is patchwise. It
Of
yeah,
one.
yeah.
Oh.
Yes. Voxels, yeah, 3D voxels.
Boxes,
Yeah.
but since it becomes warmer, the whole image influences each voxel, right? So a box is not like in a CNN now independent of other boxes.
No, yeah,
Okay,
yeah.
okay, so the right lower one.
Yes, exactly. I mean, they still do have some positional encoding where it says that you cannot have like things very far apart to like influence your representations. But yeah, you can have multiple things. And one of the important things is this tries to like get both the information, both the spatial information. So you still like frame by frame, you have like the context trying to give you the representations of the hidden parts, as well as specific time-based thing. And an important thing is the for the second part, the transformer is frozen. Like you're done with getting good representations, but now you need to train the time series part. So the transformer more or less like is very good for like static images and gets things, but for time series you have to do something slightly more, I think. So the exact architecture of this predictor, I'm not entirely sure. What is it? So you have a question?
No.
Oh yeah. I'm not entirely sure, but I assume they use some sort of CNNs or state models or state space models or something like that for continuity. So yeah, so these are like the regime of joint embedding vectors. So I'm not looking at the chat. Are there any questions on chat or from this?
Are you going to present more?
Yeah. I have some theoretical results. Like
Okay, so you want other questions from here?
Question about the two encoders. There's like an X encoder on the left for VJPA2 and then a Y encoder on the right where they do something where you kind of have a chicken and egg problem where you need like meaningful target representations for your X encoder to predict. How do you sync how do you balance the learning, preventing like the Y encoder from learning too quickly and the X encoder from learning too slowly? And are there any other tricks done outside of VJEPA for like approaching this?
oh, so you mean the encoder and the EMA encoder by X and Y, you mean?
Yes,
Uh,
yes.
oh,
Like,
yeah. That's a great question. That's a great question. These are notoriously slightly difficult to train because it can very well happen. The same problem that I mentioned earlier, like the representations can collapse. If this
exactly.
encoder encodes nothing, then this encoder can also encode nothing, and then like you can have a perfect loss, like zero loss, and like nothing can be trained. But
Yeah.
specifically, what they do is they use this EMA encoder. EMA is exponential moving average. Basically, all it is trying to do is smooth out the gradients for this encoder, or basically smooth out the weights for this encoder, and just ensure that this encoder is never exactly the same as the encoder to the left. Like the EMA encoder is always slightly different from your other encoder, and you force that with this EMA thing. And there's also like a slight caveat to this. Your loss cannot be very, very high, or the weight to your loss cannot be very high. Like you still want like some room for the representations to be different, like for the patches to have slightly different representations. But you brought up a very good point. Like it could happen that the representations could collapse, and I'm pretty sure there'll be like works coming up in the future where you use some sort of like the earlier methods, like some cross correlation between the different patches to be the cross correlation to be 0, but the correlation to be 1, and or the cross correlation matrix to be identity, basically. Like the same thing that we did for the Barlow twins or the earlier thing. I think something like that is necessary for this.
Yeah, yeah, it's interesting because that makes a lot of sense. It's surprising to me that they actually do train the EMA encoder, instead of just freezing it so that you can train something like more quickly,
So, yeah, so actually, the L1 loss does not go back to the EMA encoder. You have a stop gradient over there. So only the encoder is
Right,
trained, but the
right.
EMA encoder, and if you have like a large enough decay, or if you like decay very, very slowly, then more or less the weights are not going to be very similar at any
Ah,
point.
I see. I see.
Yeah, yeah.
Okay.
So, but yeah, there is a stop gradient over there. Otherwise, they will definitely like collapse for sure. And we have the same problem with like, so um all of these joint embedding methods, some of the tricks that you need to get them to work is have a lot of like examples, a lot of negative examples, a lot of positive examples. Like you need huge data sets, you need like specified losses and or specific like hyperparameters to those losses, and really closely monitor the training dynamics to see if things don't collapse or something like that. Uh, which is a problem that you don't have in the autoencoders. The autoencoders more or less always learn something good. So if you have a smaller data set, I would suggest definitely go for either the autoencoder based regimes and not this. And very soon you'll see why I'm saying this. But the joint embedding methods are definitely slightly more tricky to train, is what I would say. So for like, yeah, for smaller data sets or more robust training, we can go to the earlier.
Right, how much more?
Yeah, sorry.
With next week or so.
Just a little bit of theoretical results.
Okay.
I promise we'll be done soon. Sorry. So, okay, so the last thing that we want to sort of see is what we saw, that the autoencoder based regimes learned representations which were close to the principal components, right? Like, or tried to encode the maximum variance in the data. What do these models learn, or what are the representations that these models learn, the joint embedding models? So the very interesting thing is, so I won't go over the neural kernel tangent, like,
How 1%? Right.
yeah, 11. But basically, like if you go over this math, also if anybody wants to talk about the math or everything, like, yeah. The high level is that these also project the data onto the eigenvectors of the cross correlation matrix. So where is that cross? Okay. Over here, or actually, yeah, over here. Basically, this was the loss function that we used, or this was the loss function that we used to train the embedding methods, like either the joint embedding methods. And if you look at the cross correlation matrix, you basically project onto the eigenvectors of the cross correlation matrix. And now, if your augmented examples are the same as your original examples, more or less, then you get the same solution as the autoencoder based methods. So the higher level is these methods also learn very similar representations, but are highly decided by what augmentations do you use. So based on a lot of this theory, these are like some of the augmentations that you can use to get really good results or to train these models really well. And these augmentations more or less look very, very similar to the denoising autoencoder based models. So ideally, like, both the regimes more or less give you the same kind of solutions, because the cross correlation matrix is similar to the covariance matrix if like the examples are similar. But the main thing is you need to have like some augmentations. You need to have some augmentations or some sort of self-supervised task to get like good, really good representations. Like basically test the model. Like instead of just these examples, what if the examples were slightly different? Like, would you still come up with the same representation or not? So, okay, we will not talk about the generalization error bound or something, but the main thing about it is it does depend on the model complexity. Like this error is really dependent on the value of k, and the value of k is how big your representation is. So how much capacity do you give to your representation? Like your representations will really depend on that. So yeah, okay, so just finally some key takeaways. To really understand representations, we need both the optimization perspective, which is like the double descent perspective, also the statistics. Like we want to see what are like, or basically what do these representations actually encode. So they are mostly like the eigenvalues, or they mostly project onto the eigenvectors and so on. So we looked at representations from both these perspectives. Then the bottleneck effects. Complexity is really controlled by the representation dimension, not just the parameter count. So you want to also increase your representation size along with your model size. And this is critically seen if you try to train transformer models with like a much smaller dimension. The key query vectors, if you make the dimension smaller, they don't really work. I tried that. So like this theory explains that you do need higher dimensions. Then basically spectral methods emerge. Both contrastive methods and autoencoder based methods basically learn these spectral projections under some conditions. Then basically, like theoretically, you have these nice bounds about when will they be good for downstream task, when won't they be for won't they be good for downstream tasks, and so on. And then basically, yeah, there is still much more room for theoretical contribution, because you want to ideally work with smaller data sets and smaller models and make them very, very efficient. And these regimes are currently very inefficient, as we can see. So yeah, that is, yeah, that's it from me. Yeah. Okay.
Great. Some more questions? In the chat?
So I cannot
Well,
hear.
you can always send questions.
Yeah, definitely. Yeah, so if anybody wants to talk about even about the even let's say about any of the derivations or the theoretical aspects, like please feel free to reach out.